Okay, so now we're going to talk about the power of random projections. So we've talked about the curse of dimensionality, and we've talked about how it means that unless the data has some structure, we don't really have a hope of learning in high dimensions without having an exponentially large number of training examples, right? So let's assume that there is some hope, there is some low dimensional structure. I don't quite know what it is, right? We also have looked at principal component analysis using the SVD and seen that, yes, I can potentially reduce a dimension by taking the, partial SVD, just the, top few eigenmodes of the data matrix. But actually, that might sometimes lose out information that are there in other modes. So an alternative is to sort of say, okay, I hope there is some interesting low-dimensional structure. Let me just try to capture it through random projections. So I'm going to, so this general principle of sort of taking random projections to implicitly capture information, I can also call it sort of compressive projections because I'm compressing into lower dimensions. I just want to talk about a couple of examples. There's a very rich tradition of it. I'll give you something to look up more papers on. It's worth looking at sketching. It's certainly worth looking at compressive as keywords for looking at the vast literature that is there on the power of random projections. But I'm only going to talk about two very basic ideas. So the first idea is the following. So if I'm given a bunch of vectors, let me say x1 through xn, I'm deliberately using a different n from the capital N that I use for training set. This is completely arbitrary. There are these vectors. Each of them is d-dimensional. Then, and if I do a random projection of it, so I multiply it by a random matrix phi, and basically the phi is say m cross d, and I get a bunch of new vectors xi hat. So what is xi hat? Xi hat is phi times xi, I going from 1 through n, and since xi is d cross 1, let's assume column vectors here, m cross d random matrix. So this is m cross 1. Then as long as m is actually of the order of the log of the number of vectors, so, and we won't talk about proportionality constants. If m is order of log n, then the Euclidean geometry, all those relationships are preserved. What do I mean by that? I mean that in the original space you might have these Euclidean distances, L2 distances. I can choose these, if I have enough projections and only logarithmically, then I can choose, I can make sure that the projections have roughly the same distance. And of course the same goes for the inner products also, that xi xj is approximately equal to xi hat xj hat. These are essentially equivalent statements. This is for I, j, between n and 1, so including I equals j for the inner products, right? So this is a very powerful result, that you can preserve this Euclidean geometry relationships based on which you do so much training and inference by a relatively small number of random projections. And this is boxing it, the whole thing, and this is what goes by the name of the Johnson-Lyndon Strauss lemma, right? So that's the first idea that I'm going to talk about. The JL lemma provides motivation for a lot of different sketching type schemes, but one particular application that has gotten a lot of recent attention is its application to the area of compressive sensing. So let me just say what that is. So compressive sensing, let me just state the result. Basically, it says, let me say it informally, sparse vectors in high dimensional space can be reconstructed with a small number of random projections. So let's be a little more specific here. So there's X, which is d-dimensional, and we know that the number of non-zero entries of X is small. So this is small. So let's say this is K. So this is the number of non-zero entries, and we are in a regime where K is much less than D, right? Then the key result is that now if I create a projection P, this is not claiming to be X hat now. It's just basically a projection based on a random matrix phi operating on X, and again let's say this is M cross D, this is P cross 1, so it's M cross 1. Then we can reconstruct X from these projections if M is of the order of K log D. So basically you see that I need only a logarithmic number of measurements in the dimension, and then of course I need a linear number of measurements in the number of non-zero entries, right? So that's one way to state the key sort of compressive sensing result. But there's also a natural generalization which says that suppose so this is just saying it's sparse with respect to the unit basis, right? This is what this L0 norm is telling me. So now, but let me suppose that X is sparse with respect to some arbitrary basis, to some basis B, right? So this could be, this could be an orthonormal basis that is particularly well matched to the data set that X is drawn from. So I might have exactly D basis elements for D-dimensional, or it could be over complete. It could be BD. These I could have D bigger than D. Then the BIs need not be orthonormal. They could be linearly dependent. I could have any sort of model like this, but the basic property that I assume is that X can be expanded with respect to the basis where this is sparse, right? And then the same result holds, that essentially if I look at P equals phi X, that is phi BS, right? Then I can reconstruct S from P. So what am I saying? I'm saying that I have a linear regression problem where let me change pen color, where P is the target. This is like my data matrix. Let me call it phi hat, and I'm saying P is equal to phi hat S, and S is sparse, and I can reconstruct. I use some sort of sparse linear regression to get S hat, and then I use my model to get X hat, which is PS hat. So that is the key idea of compressive sensing, that I can, with a relatively small number of random projections, scaling K in the linearly in the sparsity order k and only logarithmically in the ambient dimension, I can reconstruct this. And how do I reconstruct it? I can reconstruct it using a lasso problem or a matching pursuit or orthogonal matching pursuit. Any technique that you use for sparse linear regression works. So let me tell you a two specific examples in which these ideas can be used, and then we'll get into the sort of the theoretical rationale behind these results. We won't have time to go through the entire derivation. For that, you have to read the relevant papers, but the core ideas we will get. So let me reiterate that two general things that you can do with these random projections. One is sketching. And again, let me put it in a context that we have been working with. So I have data points x1 through xn, and they are all sort of d-dimensional. And I create these projections, pi, which is phi times xi. Now I'm thinking of these data points as column vectors here. You change your convention based on the literature you're working with. So in much of the signal processing literature, we think of the data points as column vectors. So these are now m cross 1, m cross d phi, and then d cross 1 this guys. I equals 1 to n. And then I do downstream inference based on downstream learning and inference, right? Learning and inference. So, for example, you might do k-means on the PIs or EM algorithm. If you're doing unsupervised learning, you might actually feed it to a DNN. You could do a DNN. Everything you can do in reduced dimensional with the reduced dimensional sort of data points, PI, right? And how big should the dimension of m, of the PIs be? Well, it's sort of it depends on the application, and in the particular context of the JL lemma, you saw that log of the number of points is good enough. But really, the specific analytical prescriptions differ based on the settings. And how should the phi matrix be chosen? Well, a very common choice is to choose every element in phi as, say, zero mean Gaussian, or you could choose phi ij equals plus minus 1 with probability half, so you could choose them to be symmetric Bernoulli. The paper that is our main reference for exposition of the Johnson-Lyndon Strauss lemma, in the handout, they also consider a phi where there's a bunch of zeros there. So phi ij is 0 with probability 2/3, plus 1 with probability 1/6, and minus 1 with probability 1/6. So generally speaking, IID mean 0 and finite variance entries work. Generally speaking, we also normalize the variance to 1. This is already normalized to 1. This is not quite so, but yeah, that's the usual choice we make. And as we'll see, it's a fairly general result. The JL lemma that provides some sort of a backdrop for all this is a rather general result that works for many different choices of phi. Okay, so sketching is one application, and the other application we already discussed what the framework is, compressive or compressed sensing. And let me just quickly review that. Our model is that I have a vector x, and now unlike the sketching setting, we actually have some knowledge of the structure of S, right? So basically I know a basis with respect to which x is sparse. So I can write x as b times s, where this is sparse. So, and then of course this is d cross 1. And then what we are saying is that if I have a projection P, which is phi times x, which is of course phi times b times s, then I can solve a sparse linear regression problem. For example, I might do something like, remember P is m cross 1. So I have essentially these m targets that I'm trying to hit by choosing this regressor S. So these are the targets. This is the regressor, and this is playing the role of the features that that I'm using to explain the targets. And so one example of reconstructing things might be I have a quadratic cost function P minus phi hat S squared plus L1 constraint on S. And I might, just like I did before, to make sure that this Lagrange multiplier doesn't depend on the number of measurements, in this case m, I can normalize by 1 over 2m. So this, let me change pen color. I could solve a lasso problem to do it. Or I could use orthogonal matching pursuit on the same model, P equals phi hat S. I could use matching pursuit or orthogonal matching pursuit on it, right? So that's sort of the compressive sensing application. So those are the two applications, and here m should be of the order of k log d, where k is the sparsity level. So k is what I think the ballpark of S0, I mean the L0 norm of the sparse explanation is going to be. So that tells us how to apply these random projections in two examples, but let's now understand why these things make sense, at least get some idea of why these things make sense. Okay, so let's start with the JL lemma, the Johnson, Lyndon, Strauss lemma. Recall what it says. Basically, if you give me d-dimensional vectors xi, say little n of them, and I have these projections phi xi, the random projections, then and these are m cross 1, so this is m cross d, and the claim is that we can make x hat I minus x hat j approximately equal to xi minus xj for m, which is order of the log of the number of points. So it does not depend on the dimension. Okay, that's an amazing actually result. Of course, this result only holds as the dimension and the number of measurements gets large, but even so, it's a pretty impressive result. So let's assume that phi ij are independent and identically distributed, zero mean, and they have been normalized to unit variance just for simplicity. And let's see what happens to an arbitrary unit norm vector u in the d-dimensional space when I project it. So let's say we have normalized u to unit norm just for simplicity. And let me define u hat as phi times u. And let's try to figure out what the norm of norm squared of u hat is going to be. So let's look at a particular entry, u hat I. That is just phi ij times uj. I'm summing over these d components of the u, right? Well, this is a random variable, right? This is because the phis are random, this is a random variable. let's look at its mean and variance. So the mean, well, that is 0 because the mean of the phi's are 0. So the expectation goes inside the summation. These are random. This is not. This is just 0. What about the variance? Well, if the mean is 0, the variance is just equal to the square of the thing, right? So basically is expected value of ui hat squared. And so I'm just going to take the expected value of summation j equals 1 to d phi j uj, and I need a different dummy variable of summation to make sure I count all the terms. So j prime equals 1 to d phi j prime uj prime, right? And all the cross terms will drop out, right? So I have, let me just do this. J equals 1 to d, j prime equals 1 to d, taking the summations outside the expectation or taking the expectation inside, group the random terms together, phi j times phi j prime, then uj prime. And remember, these guys are IID and zero mean and unit variance. Since there's zero mean, this expectation decomposes into the product of expectations for j not equal to j prime, and those means are 0. So this is equal to expected value of phi j times expected value of phi j prime when j is not equal to j prime, and so this is equal to 0 in this case. And of course, for j equals j prime, this is just the square of the phi j squared, and this is equal to 1 since it has 0 mean and unit variance for j equals j prime. So the two summations collapse into 1 because I only get non-zero results for j equals j prime, and so I get j equals 1 to d 1 times uj times uj, right? So this is the L2 norm squared of u. That's what the variance of ui hat is. The other thing to note is that ui hat are independent for I equals 1 to m. Why? Because this depends on different rows. So different rows of phi j are considered of independent random variables. So they are independent, right? So now, so you see that the information about the original norm squared of u is buried in the variance of each of these guys, right? In the this is actually equal to the norm squared of the original vector u before projection is actually equal to the expected value of each of the ui hat squares, right? So if I want to get an estimate of this guy, which is, I can just average them. I've got a bunch of independent random variables, m of them to be precise. And if I average them empirically, this average by the law of large numbers will tend to basically the norm squared of the original vector u, which we had conveniently normalized to 1, but that's what it turns out to be. So that's observation number 1. How fast do they go to this norm squared? How quickly do they obtain this average? So that's an interesting question as well, because we kind of have to review something about it. So here, what did we do here, and what does this tend to mean? What we are actually doing here is applying the law of large numbers. And this convergence is sort of with the strong law of large numbers, this convergence happens with probability 1. If you don't know exactly what technically with probability 1 means, that's fine, don't worry about it, but it's a very strong form of convergence. We also need an associated result. Let me take a sidebar and state it actually. So let me come up with a different notation. So let's say Z1 through Zm are IID random variables, and they're nice, basically finite variance and things like that. And the strong law of large numbers says that their empirical average tends to their statistical average, right? That's one thing. And this is with probability 1. Again, don't worry about it if you don't know what that means. And let me call this Z bar, the empirical mean of these guys. The other very strong result is that the probability that the Z bar is different from the statistical mean, that the empirical mean is different enough. So suppose it's the difference, the magnitude of the difference is bigger than epsilon. That goes down exponentially with the number of terms you're averaging. So it's exponential e to the minus m times some constant. And that constant depends on epsilon, depends on the distribution of z and all that kind of stuff, right? And this constant, again, we don't have time to go into it, but this constant is can be computed using the so-called Chernoff bound. So I'll leave it to you to look it up if you're interested. But this is the result we need, and this particular thing, I need only the less than or equal to part, but this is actually asymptotically exact in some in some sense, and I'll let you look it up under the keyword large deviations. So large deviations is intimately related to the Chernoff bound, but I only need the Chernoff bound part of it, this result right now. Okay, now that we have taken that sidebar, let's go back to our problem, where what we had was that these UI hats were IID, zero mean, with expected value of UI hat squared being this desired L2 norm squared that we want to approximate with these randomized projections, and we had that if I average these guys, U1 hat squared through UM hat squared, that's going to tend to this U2 squared, right? Basically the norm squared of the original vector, and this was the law of large numbers. And now I'm going to apply the Chernoff bound and say that, oh yeah, well, this by the way, let me start writing this down for what it is. What is this? This is just the L2 norm of the projection you had, right? So this is just that. So what are we saying? That the Chernoff bound type thing will say that 1 over m times the L2 norm of u hat, that if I deviate it too much from the L2 norm of the original vector, so too much meaning let's say it's greater than epsilon, that will be decaying exponentially with m, the number of measurements, times some constant that depends on epsilon, right? That's what we are saying. So remember now that we were interested in approximating these distances between the original vectors, right? Distance squared, let's say. So we were interested in approximating this. So let me just look at a normalized version of this for a given pair. So I have this pair normalized by its L2 norm. So I'm going to apply the result we had for this U. How many such pairs are there? So basically I, J go from 1 through n, and I'm looking at distinct pairs. Remember that the L2 norm square doesn't depend on whether it's xi minus xj or xj minus xi. So there are n choose 2 such pairs, right? That's what we have, right? And so now I'm saying, my projections actually have the right, are pretty close to the right answer. For any of them, the probability that the projection is straying from the right answer goes down exponentially. So what's the probability that the projection, is bad for any of them, right? Well, there are n choose two such pairs, and the probability that the projection deviates by more than epsilon is bounded by e to the minus mc epsilon, and this is a union bound that any pair is approximated badly, that the distance between any pair, badly meaning beyond that epsilon that I had talked about, right? And I want this to be less than some number, less than some delta. So you can see that if I take log on both sides, that this term looks like n squared over 2, roughly in a ballpark. So basically I have sort of a log n term there, 2 log n if you want to be precise, times minus m times c epsilon is less than sort of log of delta. And so you can see that m being order log n with the right constants will make sure that this union bound is small enough. So what have we just argued? So we took all these pairs, right, U's which were xi minus xj normalized. The U hat for this is, I'm just going to project everything, so it's xi hat minus xj hat divided by the same normalization. And what I'm saying is that even once I take the union bound and everything, so basically I'm bounding the probability of bad things happening by delta. So we are saying with probability bigger than 1 minus delta, good things happen. Good happens. What is good? It means that my u hat square over m minus L2 norm squared of u, that is less than or equal to epsilon for every pair. Okay, that's what it is saying, right? So what is, and reminder again what u hat is, it's this phi xi minus phi xj over xi minus xj. So my u hat squared for a generic pair is going to be phi xi minus phi xj whole squared over xi minus xj whole squared. And of course I've created these u's. These are all normalized to unit norm, right? The way I've constructed them. So this is these are just 1. So what have we shown? That phi xi minus phi xj squared over xi minus xj squared is between 1 plus epsilon and 1 minus epsilon with probability bigger than 1 minus delta if I have a large enough number of projections, if m is equal to order log n. So that is the statement that we can make based on our arguments, and I guess this is the formal statement, still fairly informally said, of the Johnson-Lyndon-Strauss lemma. So as I said, the J lemma has very broad implications, but a specific application is to compressive sensing, right? So let's set that up, and let me just state the result in the simplest possible terms, not with an arbitrary basis but with the unit basis. So this x in a high dimensional space is known to be k-sparse. So basically x, the L0 norm of it is less than or equal to k, at most k non-zero entries. And then again I take a random projection matrix, P equals phi x, again m cross t here, phi, and x is t cross 1, so this is m cross 1. It's fine, and this is random, like we had talked about before. Then the key result is that we can recover x from these projections with high probability, as long as the number of measurements is linear in the sparsity level and only logarithmic in the number of dimensions, right? So that's the main compressive sensing result. And let's just, the original proof of this by Candace et al. Used different techniques, but then a later paper by Baraniuk et al. Elucidated the relationship between this and the JL lemma very clearly, and so that's what I want to sketch here for you. So the key intermediate result that sort of allows us to recover x from P is the so-called restricted isometry property, often called RIP, which says that this many m equals order k log d projections preserve the Euclidean geometry, preserve Euclidean distances between k-sparse vectors. So for the specific scenario where you know that the vectors are k-sparse, and of course there are infinitely many of them, so it's not a direct application of JL lemma as you can think, because JL lemma works for a finite number of vectors, but so there are infinitely many k-sparse vectors, but m equals order k log d projections preserve in the sense we talked about, within some approximation with high probability, etc., preserve these Euclidean distances. So you can intuitively see why the RIP is important for recovery. Basically, if you don't preserve Euclidean distances, how are you going to distinguish one k-sparse vector from another based on a particular set of measurements, right? So you can see why it would lead to that recovery result, but we are not going to make that connection here. All we're going to say is, why does the JL lemma lead to the RIP? So the JL lemma works for a finite number of vectors. So the key idea is, cover the space of k-sparse vectors by a finite number of vectors. So basically, construct a finite set of vectors such that any k-sparse vector is close in the Euclidean sense to one of them, at least one of them, right? So that's what covering means. And then basically say, okay, I'm going to use JL to enforce Euclidean distances between between pairs in this finite set of vectors, and the set of k-sparse vectors will inherit that property, right? So there are a lot of details there, but let's see how this covering can happen. So if you know which of the k entries are non-zero, and if you focus on just on this, you have a k-dimensional subspace, right? Once you know which set of entries are allowed to be non-zero, how many such subspaces are there? Well, the number of ways in which you can choose k dimensions out of D. So there D choose k number of such subspaces. So that's observation number 1. Also, without loss of generality, you can normalize all vectors to unit norm, right? So let's just do that. So now for each k-dimensional subspace, consider the unit sphere, right? Basically, k-dimensional sphere, and say, okay, I can approximate it to, I can find how many little spheres of radius epsilon do I need to cover this unit sphere. Well, in k dimensions, the volume of a sphere of radius epsilon scales with epsilon to the power of k with some constant that depends on k. So and the volume of the unit sphere scales with 1 to the power of k times that constant. So basically, order 1 over epsilon k vectors are needed to cover the unit sphere in one subspace. In one subspace, right? So what's the total number of vectors that are needed? It's of the order of D choose k times order of 1 over epsilon to the power of k. That's the number of vectors that's needed. So that's the n for which I'll apply my JL lemma. Now, D choose k, I'm just going to do fairly brute force approximation as D over k to the power of k, and then epsilon to the power of k is just there and there. So this is of the order of that. Of the order of that is the number of vectors whose Euclidean distances I need to preserve. And by the JL lemma, I need order of log n such random projections needed by the JL lemma. So what's that? That is, I'll just take the log here. So this is order k log D over k plus k log 1 over epsilon. So I guess it depends how well you want to approximate things and all that, but really the dominant part that grows with dimension is this, and note that it only grows logarithmically with the number of dimensions. So that is the key idea, that basically you only need that many projections to preserve Euclidean distances among these k-sparse vectors. Hence, when I give you the projections, you can use sparse linear regression to find the right one. So that's sort of the essence of the argument behind compressive sensing. And we've already talked about how to apply these ideas for, in both the sketching and compressive sensing context. So that's all I'm going to say about this general area of random projections and how they're used to in these contexts. There's a lot more you could find out. There's a huge literature on it, and definitely worth exploring for those who are interested in such things.